In problem 6, just like in problem number 5, we're just writing the system of equations associated with the augmented matrix. And so I just wanted to show you that if we see 1, 0, 0, negative 4, you don't have to write x plus 0y plus 0z equals negative 4. You can just leave out any of the variables associated with the coefficient of 0. So that's how we would write the system of equations associated with the augmented matrix. Anyway, so then when we get to numbers 7, 8, and 9, we're determining whether or not the system corresponding to the given matrix is consistent or inconsistent. And if you remember, we talked about a linear system having no solution would be considered inconsistent. So if we find that it has no solution, we would say, oh, it's just inconsistent. But if it does have a solution, we would say that it's consistent. And so anyway, what we would do here is we would work our way back from the bottom to the top. In this first equation here, in this first equation we're going to write, all we have is zeros here. So we have 0z equals 9, and so 0 times anything is 0, and we get 0 equals 9. That's never true. And if we get a statement that's never true, we would say, therefore, the system is inconsistent. So there's not much work to do there. On the other hand, if we see down here, we have z, 1 times z equals 5. And so what we do is we take the z equals 5, and we're going to replace z in the second row with 5. And we see we have 3y plus 2z equals 7. So that's the second row. And we're going to take our z equals 5 and substitute it in for z. Here we get 3y plus 2 times 5 equals 7, and we just solve for y. So we work our way back, starting with the row that has the fewest number of entries, and then we continue to substitute back in until we get to the first equation. We find x, y, and z. So we have 3y plus 10 equals 7. If we subtract 10 from both sides, we get negative 3. Therefore, y is equal to negative 1 if we divide by 3. Then we're going to take negative 1, and let me put circles around these. We're going to take 5 and negative 1 and replace in the first equation for y and z. So in the first equation, we get x plus 2y plus 2z. I would recommend definitely writing that out. And then doing your substitution. X plus 2 times y, which is negative 1, plus z, which is 5, equals 3. And what do we have here? We have minus 2 and a plus 10. So that's plus 8 equals 3. And when we subtract 8 from both sides, we get x equals negative 5. And so we get our three variables solved for. And so therefore, we would say the solution is x, y, z, negative 5, negative 1, and 5. And so writing our system of linear equations as an augmented matrix, it helps us to simplify the process, and so we can see it's just a lot simpler than having to write an x, y, z at every single equation. And so it's a really, really helpful tool to be able to do that. And then finally, for number 9, in the third row, we see all zeros. And so basically, what that means is we have 0 times z equals 0. So we actually get a statement that is true. That's true. If it's true, that means that we can choose z to be any number. And if z is any real number, then we replace in the second equation. So we have y plus 3z equals negative 4. If z can be any number, we don't pick a number for z. We just keep it as z. So in other words, we solve for y in terms of z. So y is equal to negative 4 minus 3z. And then when we replace z in the first equation with just z, we have x, so 1x minus 2z is equal to 5. So we're just going to put z into the first equation as well, solving for x. So we get x equals 5 plus 2z. So basically, a system like this actually does have a solution. It's consistent. It's just all dependent upon what the value for z is. And so the way we write that is our x-coordinate is 5 plus 2z. Our y-coordinate is -4 minus 3z. And our z-coordinate is just z, where z is any real number. So there are an infinite number of solutions to this system of linear equations. And we can see that, again, there's a lot less work involved when we have our system of linear equations written as a matrix.